Hello learners, I am Dr. Subodh Kersharwani working with Indira Gandhi National Open University in the School of Management Studies. The topic which I am going to talk today is Bayes theorem, which is part of our the course called MCO3 research methodology under the ambit of probability, and we have talked a lot about concepts of probability, various distributions of probability, and then we are focusing on the Bayes theorem. So going into the depth of this Bayes theorem, one of many applications of Bayes theorem is Bayesian inference, a particular approach to statistical inference. When applied, the probabilities involved in the theorem may have different probability interpretations. With Bayesian probability interpretation, the theorem expresses how a degree of belief expressed as a probability should rationally change to account for the availability of related evidence. Bayesian inference is fundamental to Bayesian statistics. Bayesian statistics is a mathematical procedure that applies probabilities to statistical problems. It provides people the tools to update their belief in the evidence of new data. So this video of this head brings to derive and intuitively explains Bayes' law. It shows how the observation that joint probabilities can be calculated based on the conditional probability of A given B as well as B given A leads to Bayes' law. So there is an edge of Bayesian theorem when you are comparing with statistics. The drawback of frequent statistics lead to the need for Bayesian statistics. Discover Bayesian statistics and Bayesian inferences. There are various methods to test the significance of the model like p-value, confidence interval, some other etc. Bayesian statistics continue to remain incomprehensible in the ignited minds of many analysts. Being amazed by the incredible power of machine learning, a lot of us have become unfaithful to statistics, and that is the reason which have given S to Bayesian theorem. So when should we use Bayes theorem? That is a very important question. The Bayes theorem describes the probability of an event based on the prior knowledge of the conditions that might be related to the event. So if we know the conditional probability, we can use the Bayes rule to find out the reverse probabilities. So why is Bayes rule so important? Bayes theorem provides a way to revise existing predictions or theories, update probabilities given new or additional evidence. So in finance, Bayes theorem can be used to rate the risk of lending money to potential borrowers. So as far as this particular course which I was talking about, MCO3 research methodology in statistical analysis, which is for the commerce student, which is for the postgraduate student. So this financial aspect, if you are talking about, this theorem is going to be quite useful for the learners who are pursuing their Master of Commerce. So quite as far as the finance is concerned, as far as risk lending money is concerned, this is going to helpful to them in a big manner. So in probability theory and statistics, Bayes theorem, alternatively Bayes law or Bayes rule, named after Reverend Thomas Bayes, describe the probability of an event based on prior knowledge of conditions that might be related to the event. For example, if the risk of developing health problems is known to increase with age, Bayes theorem allows the risk to an individual of a known age to be assessed more accurately by conditioning it on his age than simply assuming that the individual is typical of the population as a whole. So if you go into the backdrop of Bayes theorem, as far as the equation, as far as the mathematical formulae is concerned, it allows us to manipulate condition probabilities for two events A and B. Bayes theorem let us to go from probability B given A to probability A given B. If we know the marginal probabilities of the outcomes of A and the probabilities of B given the outcomes of A, here is the equation for Bayes theorem for two events with two possible outcomes, A and not A. So probability of A given B is equals to probability of B given A multiplied by probability of A, and that could be divided by probability of BA multiplied by probability A, and we are going to sum up with the probability of BA with the probability of A. So that is the formula which can be come up on the screen of the learners, and by that you can able to formalize the Bayes theorem. So how to update probability of occurrence, that need to be answered. Prior probability, that is pi is equal to prior for theory I, posterior probability, updated probability for theory I, tumor classification, handwritten digit character recognitions, and probability class I. These are the terminologies which we are going to take care in a coming slides, and we are going to distinguish also what is the difference between prior and posterior. So let's take an example. I think since we all are going through the pandemic stage. So probability of positive corona is 0.98. Suppose ABC is tested positive, what is his chance that he has HIV? So 0.98, what other information is needed? So that is where the things are going to be there. How can we integrate multiple data sets? So published data, genetic data, expression data, and then evolutionary data. So you see how we are going to integrate data when we are going to do that. And what is Bayesian approach to statistics? So Bayesian statistics assign probabilities to a model that gives us tools for calculating probability of model with respect to data, and we will see that this cannot be done without assigning a prior probability to each model. We update the model probabilities in the light of each data set rather than imagining many hypothetical experiments. And in philosophy of science, we do not rule out models, just determine their relative probabilities. So if we talk more about the Bayesian theorem, suppose we have estimated prior probabilities for events we are concerned with, and then obtain new information. We would like to sound a method to a computed revised or posterior probabilities, and Bayes' theorem give us a way to do this. So as discussed earlier, the basic objective of calculating probabilities is to facilitate us in decision making. For example, assume that you are a seller of winter garments. Obviously, you are interested in the demand of winter garments. To help you in deciding on the amount you should stock for this winter, you have computed the probability of selling different quantities and have noted that the chance of selling a certain quantity is very high, and accordingly, you have taken the decision to stock a large quantity of the product. So suppose when finally the season ends, you find that you are left with a large quantity of stock, and then you feel that the earlier probability calculation should be revised given the new experience to help you decide on the stock for the next winter. And similarly, situations exist where we are interested in an event on an ongoing basis. So every time some new information is available, we revise our probability, and this revision of probability with added information is formalized in the probability theory in terms of theorem called Bayes' theorem. And Bayes' theorem offers a powerful statistical method of combining our evaluation of new information as well as our prior statement of the probability to create posterior probability. So thus probabilities before revision by Bayes concepts are termed as priori probabilities, and probabilities which have undergone revision in the light of additional information by Bayes rules are termed as posterior probabilities, or revised probabilities which can be altered after additional information is gathered. So we will take into consideration these two terms in a more elaborative manner with the help of certain examples and certain pictorial presentations, so that the learners will get a clear view about what exactly the distinguishment between these two terms, that is priori and posterior. So these probabilities before revision by Bayes concept termed as prior probabilities, and probabilities which have undergone revision in the light of additional information by Bayes rules are termed as posterior probabilities, or revised probabilities which can be altered after additional information is gathered. So what is Bayesian approach to statistics? How does it differ from frequentist approach? Conditional probabilities, we have already have a very elaborative sessions, maybe in a coming days when we are going to talk more about probability distribution. Under the ambit of that, we are going to talk more about the conditional probability, either it could be with respect to the dependent variable or independent variable. So Bayes' theorem, priori probabilities are there, and examples of applying Bayesian statistics and Bayesian correlation testing and model selections are also need to be taken care. So if you see this particular image, you will find out that Bayes process is at the center of the thing, where priori probability is there, then new information is coming up, and then afterwards you make a sequel of that which is considered as a posterior probability. So this can be also explained with the another example, another view, where you see that Bayes theorem is there, then likelihood, data, priori is there, and finally posterior distribution is going to be created. So you see how the graph is going to be helping and how the data is going to be fruitful for that. So a priori and a posteriori are Latin phrases used in philosophy to distinguish type of knowledge, justification or argument by the reliance on empirical evidence or experiences. A priori knowledge is that which is independent from experience. In Bayesian statistical inference, a priori probability distribution, often simply called the prior of an uncertain quantity, is the probability distribution that would express one's belief about the quantity before some evidence is taken into account. Priors can be created using a number of methods. For example, include mathematics, tautologies and deductions from pure reason. So if you have a tabulated comparison between the posteriori and priori, you will find out that synthetic and analytic is the important ingredient. If you talk in terms of synthetic, the posteriori is going to give the true value for now but could be different. That is, chilies are hot, speeding is dangerous, contingent but useful, vivid. Whereas on the other hand, if you talk more about the priori with respect to synthetic, is prompted but not proved by the experience, which is true, independent where independently of experience, that is mass, the categories of Kant, cause, substance, etc. So discoverably use informative necessary structure or experience of the word. And if you talk in analytic term, I think null is there, and when you talk in a priori terms, self-evidently true, necessary, wholly independent of any admixture of experience, subject contains predicate, bachelors are unmarried, like these are the things which can come under that. So aims to understand the difference between a priori and posteriori is very important. A priori before does not start from experience, a posteriori is considered the after experience is needed. Focus on the word prior and posterior to help you remember which way around they are. So this is a way by which we are going to if you talk about the posteriori, knowledge is obtained through experience, whereas in priori, knowledge is obtained by analyzing concepts independent of experience. So priori knowledge which proceeds from theoretical deductions or making assumptions, not from experience or observations, whereas posteriori is knowledge which proceeds from experience or observation. So if you have a formula where probability of A and B is considered as a posterior, the probability of A being true given B is true, and likelihood is the probability of B given true given A is true, the probability of A being true, this is the knowledge, and the formula is this, and likely if you see the priori formula, posterior formula is probability of A and B equals to probability of B oblique A, that is B given A multiplied by probability of A multiplied by probability of B. So here you see this particular formula where you will find out that likelihood is considered as probability of B given A, prior is probability of A, and probability of B is marginalization, the probability being B being true. So this is the way by which we can able to interpret the formula, and it is going to be quite useful. So if you talk, we have already talked about analytics and synthetic with the help of the matrix, and if we talk about priori, we say that 2 plus 2 equals to 4, or whatever symbols you wish to use in any situation, just because we have chosen to define arithmetic in this way, which is called formalism. And if you talk in a synthetic term, we say that 2 plus 2 equals to 4 in any situation, because it is an example of something that we can tell independent of direct experience, but that does not just follow from the definition, it is called Platonism. And if you talk about posteriori, it is in analytics it is impossible, and if we say in synthetic, it is called empiricism. So we say that 2 plus 2 equals to 4 in any situation, because we have experienced instances of this truth and have generalized from there itself. So this is a way by which the graph is going to be portrayed, and it could be in the bell shape, but the shape of the priori belief is this. You find out the shape is this and when you have taken evidence, and then the posterior belief is somewhat over and above to that. So this is the way of interpreting the posterior and priori belief as far as the Bayes theorem is concerned. So Bayes theorem is more talking about with the formula P probability of A given B, which is probability of B given A multiplied by probability of A divided by probability of B, where P A by B is probability of A given observation B, and probability of B oblique A is probability of observation of B given A, and PA is a priori probability of A, and PB is the probability of the B is observed, and Bayes theorem deal with inverse probabilities. So now, what is Bayes' approach to statistics? An important rule is played by Bayes theorem, which can be derived from elementary probability, and the formula which I have already quoted in the past also, P probability of A given B is equal to probability of B given A multiplied by probability of A divided by probability of B. And if you talk about in In a different mode, I think probability of A intersection B is equal to probability of A given B multiplied by probability of B equals to probability of B given A multiplied by probability of A. So this is the formula, and by this we can able to do that. So now the thing is that since we have talked a lot about conditional probability, or we are going to talk about the conditional probability in our forthcoming session under the ambit of probability distribution, I think the question which comes in our mind is that, is Bayes' theorem conditional probability? Now Bayes' rule is used to calculate what are informally referred to as reverse conditional probabilities, which are the conditional probabilities of an event in a partition of the small space given any other event. So a friend tells you he had a nice conversation with someone in the train when they were traveling. So what is chance that other person is a woman? So your friend only tells you that the person has long hair, and does this change the previous probability? If you go say 75% women have long hair, 15% of men have long hair. So this is the way the example is going to be taken care, and there are some more examples which are there, like a consulting firm submitted a bid for large consulting contract. The firm management felt it had a 50-50 chance of landing the project. However, the agency to which the bid was submitted subsequently asked for the additional information. Past experiences indicates that for 75% of success bids and 40% of unsuccessful bids, the agency asks for additional information. What is prior probability of the bid being successful? That is prior to the request for the additional information. What is the conditional probability of a request for additional information given that the bid will be ultimately successful? Compute the posterior probability that the bid will be successful given a request for additional information. So if you are going to calculate with the help of this formula, I think S1 denotes the event of successful obtaining the project, S2 is the event of not obtaining the project, and B is the event of being asked for additional information about a bid. So PS1 is equal to 0.5, probability of B with respect to S1 is 0.75, and while using this Bayes theorem to compute the posterior probability that a request for information indicates a successful bid, I think the formula is PS1 with respect given by B is PS1 intersection B divided by PS1 intersection B plus PS2 intersection B. So this is the formula, and when we put the figures and compute it, the value is coming 6.52. So in a factory this is another example which you can take. In a factory there are two machines manufacturing bolts. The first manufactures 75% of the bolts and the second machine manufactures the remaining 25%. So from the first machine 5% of the bolts are defective, and from the second machine 8% of the bolts are defective. A bolt is selected at the random, which the probability the bolt came from the first machine given that it is defective. So let A be the event that a bolt is defective, and let B the event that bolt came from machine 1. Probability of B is 0.75 and probability of B hash is 0.25, whereas probability of A given B is 0.05 and probability of A by given B hash is 0.08. So now using Bayes theorem to find the required probability with the help of the formula, we can able to calculate, and the value is coming 0.3846. So now applying Bayes theorem to cancer patient, this is another hypothetical example which we have taken, and we see what is the repercussions and what are the impact of applying the Bayes theorem while checking it. So even if 100% of patient with pancreatic cancer have a certain symptom, when someone has the same symptom, it does not mean that this person has 100% chance of getting pancreatic cancer. Assume the incidence rate of pancreatic cancer is 1 divided by 1 lakh, while 1/10,000 healthy individuals have the same symptoms worldwide. The probability of having pancreatic cancer given the symptom is only 9.1%, and the other 99.9% could be false positives. That is falsely said to have cancer positive is a confusing term when as there the test gives the bad news. So based on the incident rate, the following table presents the corresponding numbers per 1 lakh people. So if you see this table, I think what we have done, we have plotted the cancer symptom at the column 1, which is known as cancer symptom yes, no and total, and then at the row wise we have done it. So if we plot this particular formula and then make it the which can be used to calculate the probability of having cancer when you have the symptoms, I think P cancer symptom is equals to probability of symptoms oblique given cancer and probability of cancer divided by probability of symptoms, and when we put the formula, the value is coming 9.1%. So what we have observed that in the Bayesian or epistemological interpretation, probability measures a degree of belief. Bayesian theorem links the degree of belief in a proposition before and after accounting for evidence, and there are some more examples which can defend this particular theorem. And as far as the interpretation is concerned, so it is believed that 50% certainty that a coin is twice as likely to land heads than tail if the coin is flipped a number of times, and the outcome observed that the degree of belief will probably rise or fall, but might even remain the same depending on the results. So for proposition A and evidence B, probability of A, the prior is the initial degree of belief in A. Probability of A given B, the posterior is the degree of belief after incorporating news, that is B is true, and the quotient, that is probability of B oblique probability of A oblique B, represents the support B provides for A. So I think we have talked a lot about probability, starting from the curtain raiser to probability, then talking more about the different aspect as far as the rules are concerned, and then we have talked about statistics with respect to dependent variable and independent variable, and then Bayesian theorem is playing a very important role as far as the calculation is concerned. So this is all about the particular chapter, which was just focused on the preamble part of probability and part of our chapter 13, and now we are moving towards in a coming session we are moving towards probability distributions, and you will find out there are various types of distributions which are going to be taken care, either it could be conditional, marginal or joint with respect to that, and we can also emphasize more on the different aspects like the Poisson distribution or the binomial distribution or different kinds of distribution in the coming heads. Thank you very much. We will have some more thought-provoking session which can back this particular block, because this block is more emphasized on the testing, and after accomplishing this particular chapter particular block, we can able to do a lot of things in statistics, because the concept building part had been done, the academic part had been done, the research analysis had been done. Now the time had come where we are going to come out from the trend analysis and do lot of testings, and finally when the test results come, then we start making the accumulating all those tests and making a report. So this is going to give us a complete view, complete report about that, which could be the part of the forthcoming discussions which we are going to take when we are going to give the final touch to this particular course. So this is all about this probability, and once we move towards the probability distribution, after accomplishing that we can move towards testing of hypotheses. Then particular tests are going to be applied, either it could be the t-test, ANOVA test, or different kinds of tests, because with the help of these tests we are going to move towards the execution. Thank you very much.